Let's start with filters. Today we're going to start with chapter 15, basic filter responses. All right. We got basically two types of filters. We got active filters and passive filters. Now, what is the difference between an active and a passive filter? An active filter is basically a filter or a RC circuit connected to an amplifier. All right. That is an active filter. A passive filter will consist out of reactive components, resistors and capacitors and inductors. All right. That means we're going to start looking at the filters, and we're also going to design filters where we're going to make use of active filters and to get a much better drop off. All right. The first filter we're going to talk about is a low pass filter. We're going to look at the low pass filter response. They say the bandwidth is equal to my critical frequency. FC stands for my critical frequency. All right. But why only the critical frequency? Because it's going to pass from low frequencies up to a certain critical frequency. All right, here's our low pass filter. If you look at the low pass filter, we got a resistor and a capacitor. That is a passive filter, it's not an active filter. Now, if you have a look, 0 dBs is equal to my maximum value, or 1, if we work per unit. Minus 3 dB is equal to 0.707 of the maximum value. And there is my critical frequency. That means it's going to pass the low frequencies up to my critical frequency when it basically drop or is being attenuated by 3 dBs, all right, or to 0.707 of my maximum. If I look at the single pole is one RC component. If I got a one RC component, my drop off will be minus 20 dBs per decade. Now, why is it a low pass filter? Why does it work as a low pass filter? If I apply low frequency, or let's say DC, across a capacitor, what will my capacitive reactance be? Will it be high or will it be low? I'm asking, what will my capacitive reactance be when I'm applying a low frequency? What will the capacitive reactance be? It will be high. All right. That means I will have a high AC resistance and a low resistance of the resistor. Where will the largest drop be? The largest drop will be across the high resistance or low resistance? The? It will be across the high resistance. That means across the high resistance will be the largest drop. As my frequency increases, what happened to my capacitive reactance? It starts decreasing. When it's decreasing, the largest volt drop will be across my resistance, all right? If the frequency is high enough, the capacitive reactance will decrease to basically what? What's the lowest capacitive reactance we will get there? Basically 0. That means the capacitor will act as a short circuit. You can see my capacitive reactance will decrease. That's why my amplitude will also decrease. All right? You with me? What is capacitive reactance? In plain words, what is capacitive reactance? Capacitive reactance is actually my AC resistance of my capacitor. All right. Higher the frequency, the lower my reactance. All right, here they show us basically what the ideal response should look like. If I look at this, 0 dB, it will pass 100%. And if I look at the ideal response, it should attenuate also 100%. All right. If I look at the ideal filter should pass 100% and attenuate also 100% at my critical frequency. I repeat, if I look at the ideal filter, we'll pass 100% and attenuate also 100%, all right? And here they show us, depending on how many poles we use, we can say minus 20, minus 40, minus 60. The more poles we're going to use, the closer the drop-off become to the ideal. All right, there's one formula. We're going to use the lot. My critical frequency is equal to 1 upon 2 pi RC. You're going to use this quite a lot for the critical frequency. They say the critical frequency of a low-pass filter, low-pass RC filter occurs when XC is equal to R. And there we got our FC, 1 upon 2 pi RC. And they say the critical frequency is 70.7% of the input, right? That means when it drops to 70, we reach 70%, that will be my critical frequency. Any questions? All right, now we're going to look at the high-pass filter. In the high-pass filter, we would just change the capacitor and the resistor. On my input side, I will have the capacitor. On the output side, I will have my resistor. All right. Now again, if I got low frequency, what can I say about my capacitive reactance? It's going to be high. All right. When it's going to be high, largest volt drop will be across the capacitor and the smallest volt drop will be across my resistor. That's why it's doing that. And then we will come to our critical frequency. Again, 0 dBs and minus 3 dBs. By work per unit, it will be 1 and it will be 0.707 of the maximum value. Also drop off of minus 20 dBs per decade for a single pole RC filter. All right. Any questions? All right, the same formula apply for my critical frequency, 1 upon 2 pi RC. Here they also show us, if you look at the ideal filter, it will do basically that, critical frequency, and then pass 100%. And then if you got more than one pole, minus 20, minus 40, and minus 60. But we'll come to the amount of poles and design it according to the Butterworth response. The next one is our band pass filter. What does a band pass filter do? It basically attenuate, pass from FC1 up to FC2, and then attenuate again. That means we're going to pass this band of frequencies, all right? FC1, FC2, and my resonant or my center frequency. The bandwidth will be basically FC2 minus FC1. My center frequency, FO, or my resonant frequency, will be the square root of FC1 times FC2. All right. Here we use normalized values, 1 and 0.707. You can also have 0 dBs and minus 3 dB, exactly the same. All right. Any questions? Now we're going to talk about our Q factor or our quality factor. The quality factor for that filter is Q is equal to the center frequency divided by my bandwidth. Now they're going to talk about the selectivity of a band pass filter, and the selectivity will be basically determined by my Q factor. They say band pass filters are sometimes classified as narrow band when Q is larger than 10, and wideband when Q is smaller than 10. The quality factor can also be expressed in terms of the damping factor of the filter as Q is equal to 1 upon my damping factor. We will look later on we'll talk later about the damping factor. All right, here's an example. Example 15.1. I say a certain bandpass filter has a center frequency of 15 kilohertz and a bandwidth of 1 kilohertz. Determine the Q and classify the filter as a narrow band or a wide band. All right, Q is equal to FO divided by bandwidth. Is 15 divided by 1 is equal to 15. All right, my Q is larger than 10. That means it's a narrow band filter. If it was smaller than 10, it was a wide band filter. All right, there's our band stop filter. What does a band stop filter do? It passes frequencies, then attenuate this band of frequencies, and then pass the higher frequencies. That is a band stop filter. Also, 0 dB is minus 3 dB, FC1, FC2. My bandwidth will also be FC2 minus FC1. Also my center frequency, FO. All right. Any questions? All right, now we're going to look at filter response characteristics. Filter response characteristics. All right, the first one, the one we're going to use for most of our designs, will be the Butterworth response. Now, if you look at the Butterworth response, you've got a flat response and you've got a fairly sharp drop-off. You want a drop-off that's like that, but that's not always practical. We're going to look at the bezel. Bezel got a sluggish and a slow drop-off, all right? And then we're going to look at the Chebyshev, who will have the best drop-off, but due to the high gain of the filter, of the amplifier, you will notice it will oscillate on top. There will be oscillations. That's because my gain is going to be high. I will have the best drop-off in the case of the Chebyshev, but here I will have oscillations. And you don't want oscillations there when you've got a filter. That means the one we're going to use for most of our designs will be the Butterworth response. We also have a table that will give us the Butterworth values, all right? Now, as I already mentioned, when we look at this type of filters, we've got an RC circuit connected to an amplifier. When I got an RC circuit connected to an amplifier, I'm talking about an active filter, right? Not a passive filter. An active filter is when I got an amplifier connected to an RC circuit, or a frequency selective RC circuit. What type of amplifier is that? If I look at this, and you have to name that amplifier. What amplifier is that? It's a non-inverting amplifier, all right. My input and my output will be in phase. That means I've got a non-inverting amplifier connected, or RC selective circuit connected to a non-inverting amplifier, all right. And here they give us a formula for the damping factor. It's equal to 2 minus R1 divided by R2. All right, they tell us here the value of the damping factor required to produce a desired response characteristic depends on the order or the number of poles. All right, the order of the number of poles depending how many RC circuits we connect together. All right. A pole for our purpose is simply a circuit with one resistor and one capacitor. That means I've got one resistor, one capacitor, that's one pole. All right. The more poles the filter has, the faster is the roll-off rate. That means if I got more poles, the roll-off rate will become faster. If I got one pole, it will be minus 20. If I've got two poles, it's going to be minus 40, minus 60, up to minus 120 dBs per decade. They say, to achieve a second order butterworth response, for example, the damping factor must be 1,414. To implement this damping factor, the feedback resistor ratio must be. Now they want to work out that feedback resistor ratio for a damping factor. R1 divided by R2 is equal to 2 minus damping factor is equal to 2 minus 1,414, and that is equal to 0,586. They say the ratio gives the closed loop gain of a non-inverting amplifier portion of the filter, the closed loop gain of a non-inverting amplifier, and the value of 1.586 derived as follows. We know we're going to look at the gain formula for a non-inverting amplifier. It's always 1 plus the feedback resistor divided by the input resistor. All right. Now they say the closed loop gain of a non-inverting amplifier is 1 upon my attenuation is 1 upon R2 divided by R1 plus R2. And when I turn that around, that will be R1 plus R2 divided by R2. That will be R1 divided by R2 plus 1, and that's going to be equal to 0,586 plus 1, and that will give me 1.586. All right. That will be my closed loop gain of the non-inverting amplifier. All right, let's have a look at example 15.2. They state if a resistor R2 in the feedback circuit has an active two-pole filter of the type in figure 15.6 is 10 kilo ohm, what value must R1 be to obtain a maximally flat butterworth response? R1 divided by R2 is equal to 0,586. Then I know that the one resistor is 10 kilo ohm, then I can say R1 is equal to 0,586 times R2, and that will give me the 0,586 times the 10K resistor for R2, and that will give me 5,86 kilo ohm. All right. Critical frequency and roll-off rate. As I already mentioned to you, this formula, FC, 1 upon 2 pi RC, you're going to use that formula a lot. All right. Now, if I'm going to look at what type of filter do you think this will be? You see, single pole low pass circuit. It's going to be a low pass filter. All right. An active low pass filter. Only one pole because I got one RC circuit there. And there is my non-inverting amplifier connected to that. The roll-off will be minus 20 dBs per decade, and that will be my low-pass filter. And they will talk about a first order because I only got one RC circuit there. All right, you with me? And that will be an active filter. Now what we can do, if we want to get a much better roll-off rate, we can go and connect a lot of these RC circuits or active filters together, all right? That means I can take more than one of them, connect them in cascade, and by connecting them in cascade, I will get a much better roll-off, all right? Now we're going to look at the butterworth table. All right, as I already mentioned, most of our designs, we will design for a butterworth response. You see here, values for butterworth response. Now, what I want you to do, you must know this off by heart. That means this table, you must know all the values off by heart. That means I'm not going to give it to you, you must know it. Fine. Fine with you. Why not? All right. Normally I will give you the table. You don't have to go and study and know all these values. I will give you the table. But you must know how to use this table. All right. First of all, here they give us the order, first order, second order, third, fourth, fifth, and sixth order. And with the different roll-offs. If I got the first order, minus 20, minus 40, minus 60. For the fourth order, minus 80. Fifth order, minus 100. And the sixth order, minus 120. That means that drop-off will become quite sharper. All right. The more order filter I use, the sharper the drop-off. Here they will tell us the number of poles. If I look at the first one, the first order, drop-off is going to be minus 20. Number of poles is 1. The damping factor is optional. That means you can go and use any damping factor you want to use there. It's optional. You not will have a fixed value. If I'm going to look at the second order filter, roll-off is minus 40. It will have 2 poles, not a single pole, a 2 pole. The damping factor is 1,414. And the R1-R2 ratio is 0,586. That was that first thing we did and where they derived that. If I'm going to look at the third order filter, I will have my first stage will be a 2-pole, all right. Damping factor is 1, R1-R2 ratio is 1. The second stage will have 1 pole, a damping factor of 1, R3-R4 ratio also equal to 1. All right. That is, let's go and look at the fourth order. Minus 80 dBs, 2 poles, damping factor, R1, R2 ratio. Second stage, 2 poles, damping factor, and R3, R4 ratio. All right. But when we go and look at the circuits, I will show you nicely. You will understand much better. But that is the table. You're going to use it for a butterworth response. All right. Now let's go to the low-pass filters first. All right, active low-pass filter. The closed loop gain of a non-inverting amplifier, old news to you. Where did you do it? In the previous chapters. A 1 pole. There's the response. Minus 20 dBs per gate. There's my critical frequency. You can see that is a low pass filter. If I want to change to a high pass filter, what will I do? I will make that a capacitor and I will make that a resistor. All right. Now let's go and have a look at the 2-pole, the silent key 2-pole. All right, again, now we're going to have basically 2 RC circuits, all right. A 2-pole low-pass filter, also why low-pass? Because where's my output? Across my capacitor, all right. 2 resistors and the 2 capacitors, RA, CA, RB, CB. Please, mark those things like that. It's going to help you. R1, R2, all right, you with me? And here's the formula. That formula applies, for example, if RA and RB don't have the same values, and CA and CB don't have the same values, you use this formula. But normally we make RA equal to RB, CA equal to CB. Then we can use the basic formula that states FC is 1 upon 2 pi RC, because that will be a square and that will be a square, and that will, you can remove the square root sign. All right, you with me? That's a 2-pole, the silent key 2-pole, low pass filter. All right, there they just state if the values are equal, if RA is equal to RB is equal to R and CA is equal to CB is equal to C, then I can use this formula, the simplified formula. All right, let's have a look at the example. They say in example 15.3, Determine the critical frequency of the silent key low pass filter in figure 15.11 and set a value of R1 for approximate Butterworth response. They tell you a Butterworth response. That means you must use the values from the table. Now they say since RA is equal to RB is equal to R is equal to 1K and CA is equal to CB is equal to C is equal to 0,22 microfarad, I can use a simplified formula. And then I work out my critical frequency is 7,23 kilohertz. All right, that is my critical frequency. Now, they say for a Butterworth response, the R1, R2 ratio is equal to 0,586. All right. Now, then I can go and calculate the value of R1 because I got the value of R2. R2 was given as a 1K. Then I can calculate R1, and that's going to be equal to 586 ohms. All right, you with me? There it's designed according to the Butterworth response. All right. All right, now we're going to look at the cascade low pass filters. Well, I'm going to look at the third order configuration. What will I have? I will have basically a 2-pole and a 1-pole. All right. Now, please take note to help you in the exam and in the tests. How do we mark them? R1, R2, R3, R4. If I had another stage, then it'll be R5, R6. Don't go and mark them wrongly. Then the table and these things are not going to match, and you're going to make a lot of problems, or you're going to create. Same here, RA, RB, CA, CB, RA2, CA. Right. Mark them according to that. If we go and look at this one, here we've got a fourth order configuration, a 2-pole and a 2-pole. Also, RA, RB, CA, CB, R1, R2, R3, R4. RA2, RB2, CA2, CB2. If you mark them like that, and another thing, normally, if we go and look at this, normally my non-inverting input is to the bottom, and my inverting input is to the top. Now, if you're going to turn them around, the filter is not going to work, and you're going to lose a lot of marks, all right? I repeat, look, normally we had the non-inverting input to the bottom, and the inverting input to the top. You remember? Here it's turned around. Just remember that. If you're going to put them the wrong way around, what's going to happen? You're going to lose marks. And we don't want to lose marks. All right, let's have a look at example 15.4. They say for the 4-pole filter in figure 15.12b, determine the capacitance value required to produce a critical frequency of 268 Hz if all the resistors in the RC low pass circuits are 1,8 kilo ohm. Also select values for the feedback resistors to get a Butterworth response. They say both stages must have the same critical frequency, assuming equal value capacitors. All right? We got the resistor values. We got the critical frequency because they give us a critical frequency as 268. And now we must calculate the capacitor value. When we calculate the capacitor value, we get a value of 0,33 microfarad. Now, all my capacitors I'm going to make the same. CA, CB, CA2, CB2, 0,33 microfarad. They say also select R2 is equal to R4 equal to 1 kilo ohm resistor, 1,8 kilo ohm resistor. Please remember, if I'm going to give you a question in the exam on the test, I won't ask you to select those values. I will give you a value because if you have to select values, each student select a different value. That means I must go and calculate each answer. All right. That's why I will normally give you. Here they say also select that. You choose a value. I'm not going to ask you to choose a value. I will normally give you a value. All right. But then they choose the value 1,8 kilo ohms, and then they calculate the value of R1 because we got the damping factor and we got the R1, R2 ratio. They use the R1, R2 ratio and we can calculate the value of R1. Now here they say choose R1 equal to 270 ohms, and then they calculate the value of R3. All right. Using the damping factor. There they choose R1, and here they choose R3, and they calculate the values. Please take note, I will normally give you the value. I won't ask you to choose the values. All right. Now we did have a look at the low pass filters. Now we're going to look at the high pass filters, the active high pass filter. We're going to look at the active high pass filter. The only difference here, we changed our resistor and capacitor. For the low pass filter, we had the capacitor and then the resistor. For the high pass filter, we'll have the capacitor and then the resistor. All right. That means it's going to attenuate the low frequencies and pass the high frequencies above my critical frequency. All right. That is a single pole filter. We're also going to have a look at the cell and key high pass filter. One thing we must keep in mind, if I think about the ideal high pass filter, what will happen? It will basically pass all the frequencies up to, I don't know where, let's say to infinite. But what happened in practice? Why do we get a roll-off on the high frequency side? We got an amplifier. What happens in the amplifier? There's transistors. And they say inherent internal op-amp roll-off. Due to the electronic components like transistors, what happens? It will cut off on the high frequency side. All right. Because I got junction capacitance and all those things will have an influence, and then the gain will decrease. When the gain decreases of my thing, and you also got the bandwidth of that device, I will have a roll-off on the high frequency side. All right, that will be due to my amplifier. All right, there's a cell and key high pass filter. Now, as I already mentioned, what happens? We just change the capacitor and the resistors. We had, for the low pass, a capacitor, and a resistor. Now it's a capacitor, resistor. All right. You with me? You use the same table, you use everything the same. The only difference, I changed my capacitors and the resistors. All right, let's have a look at this example. Example 15.5. They say choose the values for a cell and key high pass filter in figure 15.15 to implement an equal value second order button with response with a critical frequency of approximately 10 kilohertz. They say to implement the equal value second order filter. All right. Second order filter will be a cell and key. They say start by selecting the values of RA and RB. R1 or R2 can also be the same values as RA and RB for simplicity. All right, they choose that values as equal to 3.3 kilo ohms. And now we can go and calculate our capacitor value, because we got the critical frequency of 10 kilohertz. That is my critical frequency. And then we work out the value of C. And we say C is equal to CA is equal to CB, 0.0048 microfarad. They say for the butterworth response, the damping factor must be equal to 1,414, and the R1, R2 ratio must be equal to 0,586. Where do we get that? We get that from the butterworth table. And then we can work out the value of R1. It's equal to 0,586 times R2, and R2 was chosen as 3,3 kilo ohm value, and that will give me a value of 1,93 kilo ohms. They say if you had chosen R1 is equal to 3,3 kilo ohm, then we can calculate R2, and then we get that value equal to 5,63 kilo ohms. All right. But now, if this will be a Butterworth response, all right? Cascading high-pass filters, same as the low-pass filters. The only difference, capacitors and resistors change. All right, here we got what type of filter? We got a 6-order high-pass filter. Why? Capacitors are at my input side, all right? There's a 2-pole, there's a 2-pole, and there's a 2-pole. Now, please take note. R1, I repeat, R1, R2, R3, R4, R5, R6. Mark it like that, and it's going to help you a lot. CA1, CB1, RA1, RB1, CA2, CB1, RA2, RB2, and then my third stage. All right. I'm just going to go back to the table just to show you. Now we look at the 6-order filter. That's the one drawn there. I should know my roll-off is minus 20 dBs per decade. First stage is a 2-pole. Second stage is a 2-pole. Third stage is the 2-pole, right? With my damping factor, my R1, R2 ratio. Damping factor, R3, R4 ratio. Damping factor, R5, R6 ratio. That's why I'm asking you to mark those things correctly. And let's go back to the circuit. Remember, the critical frequency for all your stages is going to be exactly the same. And then I repeat. Remember about my inverting and my non-inverting inputs. Normally, in all the amplifiers, I had the inverting input on the top and I had the non-inverting input at the bottom. Here they are being changed around. Non-inverting top, inverting at the bottom. If you put them the wrong way around, you're going to lose marks. All right. Any questions? Any questions? Right, that is all for today. Next time, tomorrow, we will start looking at 15.5 active band pass filters. All right.